In 1935, physicist Erwin Schrodinger came up with a famous thought experiment known as Schrodinger's cat. This thought experiment was designed to criticize the Copenhagen interpretation of quantum mechanics, which stated that quantum particles don't necessarily have to exist in one state or the other, but can exist in all of its possible states at once until you try to measure it. The basic setup of the experiment is relatively simple. Imagine a box with a cat, a radioactive atom, a Geiger counter, a hammer, and a jar of poisonous gas. The radioactive atom has a 50% chance of decaying within the next hour. If it does decay, it will be detected by the Geiger counter, which will drop the hammer, smashing the jar of poisonous gas and killing the cat. If the atom does not decay, nothing happens and the cat stays alive. After the hour passes, is the cat dead or alive? Our everyday logic and experiences would lead us to conclude that the cat is either dead or alive. But Schrodinger pointed out that according to the laws of quantum mechanics, the cat should be equal parts dead and alive until the box is opened. How is this possible? Since the radioactive atom is so small, it doesn't exactly behave like everyday objects. Tiny particles, known as quantum particles, can exist in a state of superposition, meaning that they exist in all of their possible states at once. That would be like tossing a coin that lands on both heads and tails at the same time. This is how electrons are able to pass through both slits in the double slit experiment. As for Schrodinger's cat, that means that the radioactive atom is both decayed and not decayed at the same time, meaning that the cat is both dead and not dead. This result seems ridiculous, and it shows how the laws of quantum mechanics can lead to strange outcomes when applied to macroscopic objects. The same laws just don't apply to everyday objects. This is known as quantum decoherence. But the idea of quantum superposition isn't completely baseless, as it does work for quantum objects. For example, it explains how photons and electrons are able to display wave behavior in certain experiments and particle behavior in others. One practical application of superposition is the development of quantum computers. Standard computers store data in binary digits known as bits. Each bit can have a value of either 0 or 1. On the other hand, quantum computers store data in quantum bits, or qubits, which exist in a state of superposition until measured. This means that qubits can have a value of 0 and 1 simultaneously. Therefore, quantum computers are able to perform complex calculations and solve problems much faster than classical computers. In today's video, we talked about Schrodinger's cat and superposition. I hope you enjoyed this video. Please subscribe, and thanks for watching.